Thank you, Tony, and good morning, everyone. The purpose of my talk today is to highlight the importance of mechanics in the development of robotics. And if you're sitting in this session, you're probably already quite convinced of that, so my task should be easy. If we look back a few decades ago, roboticists were quite successful at developing robot arms that had a significant number of degrees of freedom, appropriate workspace for different tasks. And now that we want to move much further than that, we're still facing challenges related to mechanics. So I've listed a few of them here, but there's many others: advanced manipulation and structured environments, collaboration with humans, and so on. And the common ground between, one of the common grounds between these things is that they're all related to mechanics. And that's why I say that I believe that robotic mechanical systems should be an important focus for the future progress of robotics. And I think one illustration of this is the fact that driverless cars seem to be closer to becoming a reality than personal robots that would do any kind of useful work in your house. And the reason for this is simple. Both of them require intelligence, of course, but in the case of the car, the mechanics is already there. We know how to build cars, we know how to steer them, how to propel them, but for robots that would do useful work for you, we don't know how to do all these things mechanically. So basically, one of the first questions we can ask is, what is a good design for a robotic mechanical system? I'm giving a few tentative partial answers here. There may be lots of others. First of all, I think any application should be looked at from the beginning from the mechanics point of view and try to assess the mechanical phenomena in the application. And then we should, based on that, try to exploit the fundamental principles of mechanics and not to work against them. And finally, consider mechatronics from the outset, because the mechatronic components also have some physical properties like mass, inertia, and so on. So instead of going on with these generalities, what I would like to do for the rest of the talk is to give you some examples of recent projects in the lab where we've tried to apply these principles. And I use the word try because I don't claim that we've been successful at following this approach completely. So 3 examples I will present. One of them is related to parallel mechanisms, parallel manipulators. The other one is related to cable-driven parallel robots, and the third one to human-friendly robots. So parallel mechanisms are known to have excellent mechanical properties like load carrying capacity, stiffness, and so on. But one of their main limitations is their limited orientational workspace. And this is especially true if you're looking at Gov Stewart platforms, for instance, where you have a fairly good translational workspace, but the rotational workspace is limited. One of the things you can do if you want to increase the translational workspace is to build a bigger machine. So you expand the translational workspace, but unfortunately this has no impact on the rotational workspace, which is limited mainly by kinematic singularities. So there are solutions that have been proposed to alleviate that in the literature, but they're rather specific, and they're also rather complex. For instance, this is specific to Fordov robots having an articulated platform here, and this one here uses actuation redundancy with measurement of the forces in the legs. So that's more difficult from a control point of view. So instead of doing that, we've proposed in this project to use kinematically redundant robots. So what's the basic principle here? The basic principle is statics. Those of you who are familiar with these simple planar parallel robots know that their singularities are governed by the lines associated with the legs. And if these 3 lines intersect at a common point, then you have a kinematic singularity. And it's fairly easy to see that when I start changing the orientation of the platform here, I very quickly run into such a situation. So in the literature, you will find robots like this, where you add some legs to alleviate singularities, but you introduce actuation redundancy. You have to control the forces, measure these forces, and so on. So instead of doing that, what we've done is include some kinematic redundancy. And I'm not showing you the equations, but it's fairly easy to show that the singularities are now governed by these 3 lines. This third line here is associated with this additional link. And I have 4 actuators, but I do have 4 kinematic degrees of freedom. And I can control the orientation of this link here to avoid singularity. This is what's been done in this prototype here, which you can see. The architecture of this robot is slightly different from what I've just described because it's based on the PRR architecture, but it's the same. And you can see that the rotational workspace is unlimited here because of the use of this redundancy. If I can control the orientation between the platform and the additional link, I can guarantee, not only I can guarantee that I will not run into a singularity, but I can guarantee that I will never get anywhere close to a singularity because this angle would be far away from the troubled angles. What we've done also in this work, in this prototype, we've included means of exploiting this kinematic redundancy for an additional task. For instance, here to grasp a part. So we use the redundant degree of freedom to do that. And what you see in this sequence here is that the rotational degree of freedom, again, is not limited. You can see here we can perform a full rotation and then grasp a part, whatever. So this is quite different from what you experience with conventional parallel robots. And the key to developing this was really to look at the statics of the problem. Now we've extended this to 6 degree of freedom robots, but I'd rather show you some other examples than to give you more details on that. Second example, cable-driven parallel mechanisms. They are known to have excellent properties, very large workspace because of the cables. The cables are fantastic elements. They have high stiffness to mass ratio. However, cable can only pull, and therefore these mechanisms tend to be built around their platform, their end effector. Situation is a little bit better for cable suspended mechanisms, but still we have lots of cables. So the issue we addressed here is, can we move away from the static workspace, from the footprint of the mechanism? And the answer to that is definitely not given by statics. We have to consider dynamics if we want to move outside of the static or the footprint workspace. So let's look at a very simple example. 3 cables, 3 spools. We have a point mass end effector here. If we look at the dynamics of this, we can write this equation up here, which gives us the relationship between tau, which is the tensions in the cables per unit mass of the platform, and the accelerations. G is the gravitational acceleration vector, and P double dot the acceleration of the platform. And this matrix M is simply the unit vectors along the 3 cables. So if we want these tensions to remain positive, we solve this equation for tau, and we prescribe that all components must be positive. We get these 3 constraints, and therefore any trajectory that satisfies these constraints will keep the cable under tension. So let's look, for instance, at a trajectory that would be a horizontal oscillation around a central position, and that would extend beyond the static workspace. We can describe this trajectory parametrically using these equations, just an oscillation, and we substitute this into our 3 constraints, and we obtain 3 equations that have this form. And it's very easy to see, because the BIs, we can show the BIs are positive definite, that if the magnitude of the AIs is smaller than the magnitude of the BIs, then this will always be satisfied. So if we look at the details, the BIs positive definite, the AIs look like this. And you can see these terms appearing here in each of the coefficients. Now that means that if I choose omega to be this special frequency here, these terms will be 0. And therefore the inequalities will always be satisfied. That means that if I choose this frequency to induce my motion, I can move as far away as I want from the static workspace, and the cables will always be in tension. And this is what you see in this example here. You have the 3 cables, point mass and effector. This is difficult to see, I agree. You see the point mass and effector here. We're describing this circle that extends beyond the static workspace. And we can perform the circle with no problem because we're using this special frequency, and we keep all the cables under tension. I know that you can barely see the end effector here. It's difficult to see, but yeah, you can see it when it slows down. In the next sequence, you can see a bit better because the frequency is a bit smaller, so the end effector is moving a little bit slower. And you can see that this circle, although it extends beyond the static workspace, beyond the footprint, you can perform it. So what was the key here? It was dynamics, the dynamics equations, again, mechanics. And this helped us not only to design the robot, but also to do the trajectory planning and make sure we have trajectories that are feasible. Okay, third area of application, human-friendly robots. These are a few robots that were developed in our lab for human interaction, human-robot interaction. And one of the principles that we've used is based again on statics, is static balancing. So if you see this robot here, this robot is a 4-degree of freedom device that's been designed to react to the inputs of the user to the sensitive handle here. And it can also move by itself. And you can see in the foreground this counterweight system, which is used to keep the end effector balanced at all times. That means that we can reduce the power significantly. This robot has a payload of about 200 kilograms, and the total power is less than that of a hairdryer. So you have a low-power robot, and thereby increasing the safety just by using this principle. It looks fairly simple. Now you see the readjustment of the counterweight because we're picking up some load, and we want to keep the load balanced. So this is some work that we've done in collaboration with the manufacturing industry, in this case, General Motors. Another example, this is a 7-degree of freedom robot, and this is the counterweight system here. The robot is statically balanced. And this time, the connection between the robot and the counterweight system is done through a passive hydraulic system with special cylinders that use diaphragms in order to reduce friction. So the robot is free floating, basically, and again, that allows us to reduce the power significantly. One of the observations you can make from this video is the counterweights seem to be quite large compared to the robot, and this is intentional. You can show mathematically, actually, that the larger the counterweights, the better, because the larger the counterweights, the less inertia you add to the system by including the counterweights. You can see that also on the statically balanced bridges. Last example in human-robot cooperation, this hand that we've developed for a specific purpose, which is handshaking with the robot. And so the mechanical analysis here was, what do we expect when we shake hands with someone? We expect the other person to envelope our hand, and we expect the palm of the other person to give in a little bit when we squeeze it. So we use that to design the degrees of freedom of this hand. For the fingers, we based the design on other under-actuated hands that we had developed in the lab previously. And for the palm, we obtained the inspiration from the action of handshaking. And therefore, we have this prismatic motion here, this sliding motion of the palm when we touch it, when we grasp it. One of the characteristics of the hand here is we have 2 load cells to measure these forces. So we measure the force applied by the person, and we drive the fingers in order to produce the handshake. Now this is a video, this is just a video, but I wish I could have the hand here and have you try it, because it feels really like a real handshake. You don't feel like you're shaking hands with a robot, you feel like you're shaking hands with a person. And what's nice about this is that now we mounted this on the KUKA lightweight robot, and so we can give a certain characteristic to the robot. We can give a certain behavior to the robot, and we can study the handshake characteristics based on that. Okay, I think I have, yeah, this is the mounting on the robot and the handshaking process, like you can see here. Okay, I think I can conclude at this point. What I'm trying to advocate here is the importance of mechanical systems. And I think they should really be at the core, and especially now that we're trying to target so many applications with robotics, and so many of them involve challenges in terms of mechanics. If we start with a good approach based on mechanical principles, we can only get better robots. I've also shown a few applications in different areas. There are many other areas that I could have been talking about, but I chose these specific examples to try to highlight some of the fundamental principles that can be used in the design of robots. So I think this, I know that I still have a couple of minutes, but I think I will stop at that, and we can continue with the session. Thank you very much for your attention. And I will be at the interactive sessions if you have questions or want to discuss any of these topics. Thank you.
Good morning. I'm Pradeep Ranganathan, and today I'll be talking about my work on locally weighted homographies. So here's a imaging system. Here you have a camera pointed at a convex mirror. There's very little you can assume about this imaging system because the mirror is not aligned with the optical axis of the camera. And here's an example of a calibration image that was acquired using this system. Uh, what our method allows you to do is it allows you to obtain an independent estimate of distortion in the optical system from this single image. And it lets you do this without any prior information about the intrinsics or extrinsics of the camera. And finally, it will produce a rectified image for you, uh, like the one shown here. So traditionally, one would use a homography to describe the transformation between an object and its view in a camera. And a homography is a linear transformation that in the sense that it maps lines on one perspective plane onto lines on another perspective plane. But in systems with arbitrary amounts of optical distortion, we'd like to explore a homography that can map lines onto curves, such as in this case. So the way our method works is that it uses locally weighted estimates to handle the nonlinearity. In principle and in spirit, it is similar to locally weighted linear regression. So uh, let's imagine you have a bunch of points that exhibit a nonlinear trend. What you do is you take local subsets and fit lines. And as you do this over the domain of the data, you can recover the underlying nonlinear function. So using such a technique, what we are able to do is we are able to map lines on a calibration target onto curves on the imaging plane. Such as this is an example shown here. Um, our method lets you use this initial distortion estimate to bootstrap camera calibration. And in our experiments, we are able to show that using this bootstrapping results in a more stable calibration. So, in conclusion, we proposed a new nonlinear and non-parametric homography technique, and we were able to model arbitrary amounts of distortion with this technique, and it can also improve camera calibration. Thanks for listening to me, and I'll be waiting at the interactive session to answer more questions. Thank you.
Good morning, everybody. My name is Max Mann. I'm here to report a work collaborated between the Chinese University of Hong Kong and the National University of Singapore. Uh, Mr. Wang is my current PhD student, and Hong Liang Ren was my former PhD student. And this was a visit of Mr. Wang to National University of Singapore and did this collaboration work. So it's talking about multi-robot cooperation and calibration issues. We know that in many applications, for example, payload transportation and construction, even art architecture, especially in medical applications, if you look at all the robot surgical system, it is a collaborative of many robot hands and manipulators together. So the calibration is a major issue. And the new trend in the medical application, there's many examples. And if you look at the different institutions working on different aspects. And also, we are also working on these nodes, natural orifice transluminal surgery. And you can see that this, is a natural case of multi-robot calibration, multi-robot collaboration. So the calibration issue is very critical. So if you look at the problem itself, it is actually can be modeled as AXB equal to YCZ problem. And in this problem, actually you can measure A, B, C, and you try to solve X, Y, Z simultaneously, right? And if you look at the different approaches, and there are non-simultaneous and simultaneous method. For the non-simultaneous method, you need 6 sets of data, and you solve through these procedures, right? There's a 3-step method, there's a 2-step method. And here we try to propose a simultaneous method, which solves the rotation first, and we need 3 sets of data at least. And then you solve the rotation part, right? Doing all these procedures, and then you can solve the translation part. And this way, you can simultaneously solve for X, Y, and Z. So this is, the major contribution of this paper, and this is the result. And so this is, what I want to present at this time. If you have interest, you can go to the interactive session. Thank you.
So today I'll talk about the KUKA lightweight robot calibration, which is equipped with torque sensors mounted on the link side of the actuated joints. So a good sensor calibration is necessary to get accurate measure of joint torques and to calculate accurate interaction range of the robot with its environment. And currently, torque sensor is calibrated separately by the manufacturer before it is mounted on the robot, so this is not in situ calibration. This paper gives a procedure to calibrate the sensor at the last stage of the assembling of the robot. So it allows to check the separate calibration of the manufacturer and to take into account the effect of the robot structure through its Jacobian matrix to calculate external forces and moments exerted on the end effector. The proposed solution is based on using the inverse dynamic identification model and total least squares techniques. It needs data collected on 2 trajectories, one without payload on the first video, and the other one with a non-payload. This is the inverse dynamic model, which is linear with respect to the torque sensor gains, the dynamic parameters of the links, and the inertial parameters of the payload. So by making sampling, filtering, and rewriting this equation on a total least square form, we can identify all the parameters. So the identified parameters are given here. They are very close to the manufacturer's one, and with a maximum difference of 5% on the joint 6. So this is a very good result to calibrate the torque sensors. This new method for calibration of internal torque sensor is easy to implement, and it doesn't require disassembling the robot, and it is based on using the inverse dynamic identification model and total least squares techniques. It needs only a known payload fixed on the end effector, and at the end, only the accurate value of the weight mass can be used. So this calibration method can be used on any robot equipped with internal joint torque sensors, and it allows to get accurate global identification of link dynamics parameters.
Okay, hi, my name is René Wagner. The authors of this work, Oliver Burbach and Bertolt Bäumel, unfortunately couldn't make it to the conference, so I'll be presenting in their stead. Their work is on calibrating a pair of inertial sensors at opposite ends of an imperfect kinematic chain. So the setting of this work is that we have a humanoid robot in our lab, which is mounted on a mobile platform and is supposed to perform construction tasks, as you see on the right. Manipulation is done based on data from a number of head-mounted sensors, and this requires an accurate kinematic chain from the wheels all the way to the fingertips. Now the problem with this is that the state of the last and passive torso joint, that's the one up here, is only imprecisely known. There's no position sensor, and the only way to predict its state is through a coupling to preceding joints. The proposed approach of this work is to use 2 inertia sensors, one mounted in the base, one in the head, at the opposite ends of a kinematic chain, um, for calibration. And this allows to recover the state of the kinematic chain between the two sensors under arbitrary motion. As a first step, this work defines the Hughes model and calibrates its parameters. As for the model itself, I won't go into details, but the key idea is that the mapping from one inertia sensor to the other is composed of rigid body motion of the robot, that's highlighted in red, and the kinematic motion of the kinematic chain, the blue part. Now, how is the calibration data acquired? Basically, the upper body is excited manually, and then the robot is going to drive a bit forward, then another excitement is done, and this allows to calibrate all fixed model parameters. And then the estimation is done using a nonlinear least squares optimization framework, which is available on opensam.org. It's called MTK. Here you see the rest of the sequence, so there's quite a bit of motion and quite a bit of dynamics involved. And this is basically repeating the stuff from the start. As for the results, the basic idea here is that the parameters we knew previously were re-identified correctly, and the other parameters appear to be correct too. So I'll be happy to talk to you in the interactive session after this. Thank you.
Hello, my name is Eduardo Fernandez, and I'm going to present a work about the extrinsic calibration of a set of range sensors. The extrinsic calibration of range sensors is interesting for some robot and autonomous vehicle configurations which incorporate several depth cameras, which are mainly used for navigation purposes. We are especially interested in calibrating a omnidirectional RGBD device, which consists of a rig of non-overlapping RGBD sensors, as you can see in this image. Our strategy is based on the data association from plane observations. And from these plane observations, we can establish some constraints on the relative position, the relative rotation and translation of the sensors observing a plane. The relative constraints for the rotation are based on the direction of the normal vectors, and the constraints for the relative position are based on the distance from the plane to the sensor, to the optical center of the sensor. Also, we need at least 3 observations of planes from different orientations to compute the calibration. And if more than one plane is visible at a time, we use ransack to discard outliers. The advantages of our approach is that it's easy and quick to apply. We don't need any special pattern, and no overlapping is required between the sensors, so that any geometric configuration of the sensors can be calibrated. Here, I'll show you a video. So in this video, you can see how a couple sensors are calibrated while I'm waving the sensors, observing the floor plane. In the white window, you see how the main eigenvalue of the covariance of the calibration diminishes asymptotically, which is used to stop the calibration as a convergence condition.
Good morning. My name is Young Jin from KAIS, South Korea. In fact, Yoon Soo-bok is not able to come here, so I replaced him. Today, I present new calibration method of camera laser system with non-overlapping. Many calibration methods proposed for camera and laser and sensor fusion. Because calibration is necessary to many applications, as navigation robot and autonomous autonomous vehicle and 3D construction. Previously proposed camera laser calibration method requires overlapping between camera and the laser, or without overlapping method, it needs additional camera between a laser and a camera. So it is very inconvenient. So how to calibrate non-overlapping camera laser system without extra camera? To solve this problem, we propose two methods, the plane-based method and line-based method. Sorry. Our method considers that the pattern is world coordinate, and the camera always look towards the pattern. So the calibration between camera and world coordinate is not problem. The problem is how to get calibrated camera to laser. So in the plane-based method, to obtain exchange parameter between camera and the laser, we suppose that a plane perpendicular to one of world coordinate axis. And for line-based method, it is quite similar to the plane-based method, except it needs an intersecting line of two planes. And we assume that this line parallel to one axis of the world coordinate. Simulation result with Gaussian, this is simulation result with the Gaussian noise. And this, we can figure out that the proposed method is robust to Gaussian noise. And for pose variation of translation and rotation, this result also, the proposed method is more stable than conventional method. This is our experimental system. It composed with two camera and 2D laser, because we want to calibrate simultaneously the conventional method and the proposed method. And this is experimental result show that the proposed two plane is most accurate and robust all methods. Okay. Thank you. So if you are interested, please come to my interactive section. Okay.
Hi, my name is Giancarlo Troni. I'll be presenting some work that I have done with Brian Justet at University of Michigan. This is on magnetometer bias calibration based on relative angular position measurements. So let me give you a quick review so you can learn more later after lunch. So magnetometers are commonly used to measure heading. Probably is the one that you have in your cell phone or smartphone in your pocket right now to navigate. Heading is very critical for several robotics applications. We normally use it for several things. For example, if you want to know the position of your robot, you combine heading with the speed, and you basically do odometry to estimate the position of the robot. Well, the problem is that magnetometers are highly affected by bias scale and orthogonality disturbances. So in practice, you don't get this nice motion that you command, you get something different, just due to the errors in, this is a simple bias error in the magnetometer. So the key is to perform a good calibration of your sensor on your vehicle. So previously reported method already solved this problem. In general, all require large angular movements. So to sample the full space. But in practice, in certain problems, that's not possible. Imagine you're in the middle of the ocean with your favorite underwater vehicle, and would you like to perform a magnetometer calibration? So it's not going to be possible. So for these kind of cases, we need new techniques. What we propose is using relative angular positions. So for example, coming from matching lasers, laser match scanning, or cameras, all the methods that normally use visual navigation use the main engine is basically matching images. Well, if you have this information already available, we can use it to estimate the bias of the magnetometers. So I'm not going to go through the details, but just to give you a main idea, we combine this to estimate the bias. We propose two solutions. One is offline, using least square, and the other is online, so we're estimating the bias online, and it's based on Kalman filter. There are several advantages of the methods that we propose. One of the key one is that it's not going to be it's less restrictive on the angular movement that you require to make. So it's going to be more suitable for these kind of cases on the field. If you have questions or you want to learn more about this, please stop by after lunch. I'll be happy to answer your question. Thank you so much.
Hi, my name is Jake. I'm a PhD student at Stanford University, and this project on the automatic calibration of RGBD and thermal cameras is joint work with my supervisor, Sebastian Thrun. So the motivation for this work is simple. Thermal data can help with RGBD perception. Thermal sensors are becoming cheaper, so we need an automatic method for the calibration of thermal and RGBD cameras. So in our paper, we propose such a method. In it, we assume one RGBD camera and one thermal camera, which output RGB, depth, and thermal data. We then bring the data into a common reference frame by first synchronizing the streams in the event that they have different timestamps, as they did for us, and then bringing them into spatial alignment via extrinsic calibration. The result is well-aligned RGBD-T data, where the T here stands for thermal. So in this quick pitch, I will focus on the synchronization and extrinsic calibration routines. So first, for synchronization, the main insight here is that even for these different data modalities with potentially very different viewpoints, the amount of motion in well-aligned RGBD and thermal images is relatively stable. So to make that more concrete, here we visualize the optical flow magnitude maps for the thermal and RGB images, and plot the flow statistic time series, so the average flow in an image on the right. Now, the flow statistic time series for unaligned streams will themselves be unaligned. But to synchronize, we can simply search over possible offsets and find the offset that results in the best alignment. So that's it for synchronization. And then for calibration, we just take our RGBD and thermal images and compute depth and thermal edges. Now for any given transform, we can apply that transform to obtain both edge maps in a common reference frame. For a correct transform, we can expect the edges to have heavy overlap because there's high correlation between the depth and thermal edges. So with that in mind, we form an energy that essentially measures the extent of the overlap and calibrate by simply searching for the transform that optimizes this energy. For a bit more intuition, here's an example of how an incorrect transform will result in poor alignment, while a correct transform will result in good alignment. So that was a simple example, but we've also tested our optimization routine on more complicated, difficult examples, and verified that it results in pretty RGBD data.
Okay. Good morning. I'm Jan Reda. I'm with the Autonomous Systems Lab at ETH Zurich, and I'll be presenting on spatial temporal laser to visual inertial calibration. As said in like a previous presentation, the established approaches in that field require heavy overlap between the laser and the cameras, and they, in general, like neglect the temporal relationship between the sensors. Our approach addresses both of these issues by not requiring the overlap between the camera and the laser, and by estimating a static time offset in the timestamps of the laser with respect to the camera inertial sensor. So the motivation for this work is in handheld scanning of large-scale structures, as can be seen here in this video. And by using the state from the visual inertial sensor, we can back project the range measurements and effectively like create large 3D models of indoor and outdoor structures, as can be seen in this short video. And for this, spatial calibration is not sufficient, as you can see on the left. Like if you neglect the offset between the sensors, you might end up with a bad registration of the scans in the world coordinate frame, and you get distorted models, as can be seen on the left. So we included a static offset between the two sensors, and basically like the underlying principle of our approach is the maximum likelihood estimation, where we represent the sensor trajectory as a continuous quantity and then model the laser range measurements as being induced by planes in the environment. Just to give a brief intuition about the accuracy of both spatial and temporal calibration, we recorded this video with a setup where the camera and laser field of view overlap. And as you can see here, the laser scan line can actually be perceived in the camera image. And this video basically shows our modeled scan line as pretty well coinciding with the actual perceived line by the camera. So in summary, we'll present a novel approach for spatial temporal calibration of a laser visual inertial system with a per beam error model on the range measurements. So if you have further questions, please stop by my interactive session. Thank you.
Hello, my name is Felix Andres. I'm from the Autonomous Intelligent System Lab from the University of Freiburg in Germany. And I'm presenting our catadioptric extension for RGBD cameras. So RGBD cameras have been proven very useful in robotic tasks such as indoor localization and SLAM. But in practice, they are severely limited by their field of view, not only because of the opening angle, but also because of the minimum and maximum range. The field of view of regular cameras has often been extended using mirrors. For example, this paraboloid mirror, which yields a 360-degree field of view, as shown on the right. Now, for an RGBD camera, this is not feasible because it consists of a projector and an infrared camera and a color camera. So what we propose is to split the field of view horizontally with two planar mirrors so that we get a front and a rear view. For this, we designed this structure to hold the camera and the mirrors, which can be easily created with a laser cutter from acrylic sheet. And it can easily be assembled, and the assembled thing looks like this. Now, the two viewpoints that are created from the mirrors raise the question of extrinsic calibration. And we propose an elegant solution for self-calibration via SLAM, which allows us to do full calibration of the two viewpoints from their ego motion estimate or from common observations in both viewpoints. And further, we found that we can exploit the knowledge about the device structure to reduce the degrees of freedom of the problem, which allows us to do calibration from planar motion only. Now, to evaluate the benefits of this catadioptric sensor in a SLAM application, we put it on this robot and used the laser scanner and the odometry for ground truth. But first, we went with a regular RGBD sensor through our lab with this robot and mapped the lab. And you can see that there are slight misalignments in this map. For example, the duplicate table edges, or there's a small vertical drift, which leads to a duplicate floor. When using the catadioptric sensor, we get a more consistent map with a trajectory reconstruction error that is reduced to 1/3 of the original value. And we also see that there's no vertical drift anymore. Thank you for your attention, and I hope to see you at the interactive session.
Hi everyone, and welcome to this pitch about a dual motor robot joint mechanism with epicyclic gear train. This article was written by myself, Vincent Babin, during the obtention of my master's degree, professor at the Université Laval, Clément Gosselin, and Mr. Jean-François Allan, researcher at the Hydro-Québec Research Institute. This work has been driven by the development of field robots designed for the operation and maintenance of power distribution lines on the ground. One such robot is seen here with the serial arm mounted at the end of an hydraulic arm made to be mobile in the environment. By looking at this graph, you can see the force and torques applied at the end effector during task accomplishment we see that most of the time is devoted to actually positioning the robot rather than actually applying force. So which is why time was invested in trying to reduce those positioning delays. Starting with the final product, a side-cut view of the mechanism proposed here looks like the image on the left. The proposed mechanism is a 2 degree of freedom planetary transmission mounted at the elbow of a serial robot. A simple way to see this is we are using 2 motors to drive 1 output. Should you choose to visit us at our kiosk, we shall try and make it clear how we came up with this final design. Basically, here you have the 3 basic configurations that we came up first, following by 12 new more, which is the major contribution of this paper. Sorry. We can also get more in depth how the structure of such a system can lead to a decoupling effect in the inertia matrix, hence getting easier control and more somewhat easier control. Sorry. Also, will be shown the specifics of our design, how certain design choice, and we've shown the specifics of our concept, how a planetary gear train and worm set have been put together to work in a compact environment and provide the coupling effect that would permit the 2 motors to work together and have less problem and like back driving. And finally, will be made available videos of the prototype and our simulation results. And any question you have about how we control that and many specifics about the design. Thank you very much, and hope we see you at the kiosk.
Hi everyone, I'm Kevin Hanniger. This afternoon I'd like to talk about using motion capture data to inform exoskeleton design. So, what are exoskeletons? Exoskeletons are a class of electromechanical systems which allow 2 interactions with the subjects. They allow transmission of torques to the subject and accurate measurement of the joint angles of the subject. Critical to both of these is that the point of interaction between the exoskeleton and the subject is maintained throughout the range of motion. And for this, the biological axis and the exoskeleton axis need to be aligned. This is difficult because the biological joints arise from surface contact between 2 irregular surfaces, and furthermore, in the shoulder joint, the base of the joint is not fixed, but is a member of the kinematic chain. So there may be some relationship between other joint angles and the position or orientation of the joint. So we wanted to find a relationship for that. So we used motion capture markers fixed to the humerus, at least 3 of them, and then comparing 2 frames, we assume that they undergo a rigid body transformation. This rigid body transformation by Euler's rotation theorem says that that transformation can be represented as a pure rotation about a fixed axis. By comparing multiple sets of frames, we can collect multiple axes, and taking the point most central to the collection of axes, we take that as the center of the joint. So we applied this to the subject, found the following results. As the arm is raised, elevated like this, the shoulder center roughly moves upward. And this relationship between the elevation of the arm and the position of the shoulder center is realized in a mechanism which uses a cam to raise the shoulder center of the exoskeleton in one of the directions we found of the biological joint. So another useful piece of information would be for actuator selection, knowing the maximum joint speed which would be required in normal operation. So we fixed a motion capture marker to the subject's hand, found an upper bound on the end effector speed, then knowing the workspace and the forward kinematics of the device, we found the maximum joint speed required to arbitrarily realize that end effector speed using forward differential kinematics and optimization. That's it. See you guys in the interactive session.
Good morning. My name is Alberto Parmigiani. I'm from the ICAP group at the Italian Institute of Technology. And I'm here to present our contribution on the issue of robot safety. So traditional approaches to robot safety mainly rely on two different strategies, which is one is hardware, which guarantees for inherent safety. And this is normally obtained thanks to variable stiffness actuators or serial elastic actuators. And the other solution, which is generally employed, is active control. So safety is obtained through feedback. Both of these approaches have some limitations. The first one is that has problems for what regards speed and vibration damping. And the second one, the main limitations are related to the complexity and the fact that feedback does not guarantee inherent safety. So we proposed the alternative solution based on the use of friction locking devices, which are normally used in the transmission chains of industrial machinery or wind turbines. And this element basically behaves like a torque saturator. So in our case, this is the schematic showing a normal robotic actuator with a motor, a gearbox, and a driven link. By adding this element, we can decouple the output of the robotic actuator and the driven link when the transmitted torque exceeds a certain value. This is a cross-section of the actuator. The basic point is that it does not increase significantly the dimension of our robotic joint and can be almost seamlessly be integrated in our design. This is the test setup which we used for the experiments. It's basically a modified ICAP knee, which we basically drove against the table. And this is the graph which shows that we have a consistent behavior. We can limit the torque below the 35 Newton meter level, which is the one which allows the which prevents the failure of the harmonic drive. This design has several advantages and several disadvantages. The most two relevant disadvantages are the wear of the components. So and the second one is that with some control feedback laws, you can generate a positive feedback loop, which is not so nice. So we solved the second issue, and we're working on the first one. And I'd like to see you at the interactive session to discuss this more in detail.
Good morning. I'm going to talk to you about the evaluation of robots with mixed degrees of freedom. And then you have to do the optimization to have a good performance evaluation, but there's still problems when the degrees of freedom are translational and rotational. What are the real issues when you do optimization of robots? You can find actuation redundancy. You will have also to face homogeneity problems of the operational variables. And also you need something that is close to the real robot or to specifications, industrial specifications. Then classical indexes, for instance, in the case of actuation or kinematic redundancy, sometimes are meaningless. So we are going also to deal with this problem as a consequence of the treatment of mixed degrees of freedom here. Here, for an example, you can use the characteristic lengths to do your optimization, and then you don't know really what is the significance of your result in a physical meaning. You can also find other methods in the literature. On the right side, you can have dimensionless indexes based on power, for instance, or studies in a separate way, translational capabilities and rotational capabilities. And you have to be very careful because you are also close to have a redundant robot when you do that. And that's what we are going to do in our method. but we will use a proper separation of translational and rotational degrees of freedom. And our method will be based on isotropic values and will give results that can be found on the real robot in an experimental way, and also that something that is simple to calculate. So I hope to see you after lunch in the interactive session. Thank you.
Hi everyone, my name is Hamid Azimian. I'm with the Hospital for Sick Children, Toronto. And today I'm going to talk about a new scheme that we developed for closed loop inverse kinematics under inequality constraints with application to concentric tube robots. So the idea was that we're looking for an efficient way of addressing inequality constraints in real-time Jacobian-based control, Jacobian-based inverse kinematics. This is particularly important when the robot that you're trying to control has a computationally expensive kinematics. For example, when you're dealing with a continuum robot, you have to solve a boundary condition problem in every iteration. And so the method that we used was, the idea was pretty simple. We proposed to use the slack variables to convert those inequality constraints into equality constraints. And this resulted in an augmented system. Then we're no longer just solving for the joint values, but also for the joint values and the slack variables in every iteration. And the modified equality constraint inverse kinematics problem then could be solved using task priority concept. So for example, a trajectory following problem could be defined such that the trajectory following is defined as the secondary task, while the constraints will be defined as the primary tasks. As you see, the velocity resolved solution for that can be given in a closed form, and in terms of the Jacobian of the augmented system and the Jacobian of the constraints. We applied this to the experimental setup that we developed. Actually had two tubes, and the catch is that each of these tubes actually can translate and rotate individually. The problem is that as the overlap between the curved sections increases, then the amount of difference between the roll angles will be limited to avoid the snapping motion because of the torsion. So as you see, I generated these S curves, which show you the distal roll angle versus the proximal roll angle. It tells you that if you avoid that triangular region, which is an invalid region, then you'll be safe. You won't be experiencing any snapping motion. So a trajectory following experiment, we applied this desired trajectory, and here's the modified constant. As you see that all of them have been regulated at 0, and this is the tracking error. And thank you for listening.
Good afternoon. I'm Manbok Hong from Agency for Defense Development, Korea. Currently in our research group, we make an effort to develop a lower limb exoskeleton for military use. And I'm involved in the design of joint modules, as well as the compliant module to measure the ground reaction force. What I'm going to present today is about the ankle mechanism. Compared to the exoskeletons for civilian use, the military purpose exoskeleton has the following characteristics. First, a permanent power source is now available, which means energy efficiency should be considered for all the modules of the system. Second, it has to realize fast and dexterous movements of a soldier walking on uneven and rough terrain. So each joint module should be carefully designed to minimize any mechanical constraints imposed on the operator. In this respect, the design requirements for ankle module can be summarized like this. For safe and dexterous movement, it is desirable to have illustrated rotational movement with RCN capability. In order to locate the rotation center of the mechanism closely to that of the human's ankle. And for energy efficiency and considering this torque variation of human ankle, a passive type ankle module with a power assistant capability for dorsal and plant flexion might be effective. So from the requirement, I designed this ankle mechanism consisting of this spherical fiber linkage for RCN capability and these two ankle motions, and this six-stop stereo chain with a torsional spring to provide a torque support during dorsal and plant flexion. And details on kinematic analysis and the initial prototype design will be given in my interactive session. Thank you.
Hello, I'm Tom Sihar from Osaka University. I present a novel technique to solve the prioritized inverse kinematics. The prioritized inverse kinematics is basically formalized as a quadratic programming under equality constraints. The high priority constraints are demanded to be strictly satisfied, while the error of low priority constraints are minimized under that condition. But the problem is that it is not necessarily possible to satisfy the equality constraint because even the high priority constraints can be arbitrarily given by a human, regardless of whether it's satisfiable or not. It is surprising that there is no existing solution of this problem. So far, the prioritized differential inverse kinematics has been solved by utilizing the kernel space of manipulated Jacobian. You might think it can be used for the prioritized inverse kinematics as well in an iterative fashion. But the convergence when iteratively using it hasn't been discussed. And in fact, we found it is not robust when the high priority constraints are unsatisfiable. So we propose to use a Heston's power multiplier method. It is an iterative method in which solution and the Lagrange multiplier are simultaneously obtained. It is easy to implement it by combining an unconstrained QP solver and increment of the multiplier. More importantly, it is robust as long as the original unconstrained QP solver is robust. We've already developed a robust QP solver based on the Liebenberg-Marquardt method. I don't talk about the detail now, but in our test, only the proposed method marked 100% success. So we are considering the application to human robots, such as a knee extending biped work. This is not presented in our talk, and will be presented in the next chance. So please visit me and check it out. Thank you very much.
I'm Ren Luo, and from National Taiwan University. So today I would like to talk about this analytical inverse kinematic solution for the modularized 7 degrees of freedom redundant manipulator, which we make it up with offsets on the shoulder as well as the wrist. Okay, the whole objective is to try to have this analytical inverse kinematic solution rather than only numeric. So for this 7 degrees of redundant arm. Okay, so the ingredient is to try to develop derive the closed form inverse kinematic solution with the different joints as redundancy based on the parameterization of the system or the methods. So the equations we derive are verified later on with this 7 degrees of freedom manipulator with this offsets at the shoulder as well as the wrist. which consists of modularized components, and we also have implement. So this is showing you the systems of this so-called shoulder and also wrist offsets. Okay, so we started with manipulator structures like this with a single skeleton type of systems. And of course, we need to do the DH values of these modulator structures set up. And then we define with this theta 1 up to theta 7 with these values. And then if we fixed with this analytical inverse kinematic solution, if theta 1 is redundant, so we fixed theta 1, and based on this theta 1, we derive all the equations. Okay, and then get the theta 2 and the theta 3, theta 4, and so on with this. Then we fix this theta 2, and then become theta 1 become unknown and continue and work on this redundancy derivations also. Yeah, so, okay, so and finally we get this augmented Jacobian methods, and we can prove of this what's the range of the motions based on this augmented Jacobian determined. If we determine the small and then the change of the displacement larger, which is the better candidate. For example, in here is with displacement per degree of spherical. Yeah. Okay, so we can have a verification with these endpoints and verify with whether the other configurations is also proved the same. Okay, and then this also proved the same. And the average time of computation is yeah. Let me quickly. There's no time to.
Hello, I'm Kingping T from the A-Star Institute for Infocom Research in Singapore, or I2R for short. I'm here to present this paper on behalf of my colleagues who cannot be here today. So this is a joint work between I2R and KAIST, and the main goal of this paper is to study human-guided motion learning for robots using a kind of recurrent neural network model. So the robot platform used in this study consists of a mobile base, an upper torso with 2 arms, and a pen-tilt unit holding a camera. Each arm is designed to have 7 degrees of freedom, providing kinematic redundancy similar to a human arm, and this makes it more natural for a user to guide the robot arms during the training phase. The pen-tilt vision system is required to track the position of the target object. To implement human-guided motion learning, we use a special form of neural network called the stochastic continuous time recurrent neural network, or SCTRN for short. SCTRN is utilized because it has the feature of variance estimation, which is useful for motion learning generalization. The inputs to the network are the head and arm joint angle sequences, and the network is trained to predict the output for the next time step, which is then combined with the predicted variance so as to reproduce the hidden stochastic structure of the training data. And finally, the combined output is sent to the robot in the form of target joint angles for movement generation. So during the training phase, a human trained the robot to grasp a box from different positions and then bring the object to the target position. The learning of the neural networks is done offline. And finally, in the testing phase, we see that although the box is put at initial positions that the robot has not learned before, the robot is still able to generate motion trajectories to grasp and place the object at the correct target position. So this demonstrates the motion learning generalization capability thanks to the SCTRN implementation. So for more detailed information about this paper, please visit me during the interactive session, and I look forward to speaking with you. Thank you.
Good afternoon, everybody. In a moment, hopefully, we'll have the slides up. So my name is Simon Di Maio. I'm with a company called Intuitive Surgical. I'm going to give you a quick overview of what we do, and we have a booth in the exhibit hall 219. Come by and you can learn some more. Our company develops the Da Vinci surgical system, which I'm going to try to give you a flavor of in these next couple minutes. This is what the system looks like. The cart on the left side is what's called the patient cart. This has 4 robotic manipulators that manipulate surgical instruments inside the patient's body. On the right-hand side, there's what's called a surgeon console, and this is where the surgeon sits and sees images from inside the patient's body. One of the instruments on that cart is an endoscope, and they use joysticks to manipulate the instruments inside the body. This is what it looks like. This is the surgeon sitting at the surgeon console, manipulating hand controllers and seeing a stereo view through the display. On the opposite side, on the patient side, these are the instruments following those motions. And I'll explain to you in a few moments as to why that's useful. This is the patient side. You can see the robotic manipulators facilitating that motion, following motion that the surgeon is commanding. So why do we do this? The general trend within surgery is to try to shift away from this kind of quite morbid, open surgical procedure that has some significant issues and drawbacks for the patient, and move towards something that's more minimally invasive. And so these are some examples of how a minimally invasive procedure can add value for the patient. Of course, reduced pain, scarring, less blood loss, and of course, fewer complications due to things like infection and so on. So this is an example on the right-hand side of a cardiothoracic procedure, a large incision, and below a minimally invasive approach facilitated with something like the Da Vinci robot. This is a gynecological procedure. Again, you can see the large impact of an open versus a minimally invasive procedure. This is a craniofacial procedure, base of tongue surgery, very big difference between deconstructing the face and actually getting robot arms into the patient's mouth to perform the same surgery without having to cut open the lower mandible. So what about future opportunities? Why are we here in terms of research? This is the basic anatomy of our system. You can see it's a master-slave teleoperation system. The key being that in the middle here, this control system is really software that we can use to do things like stabilize motion, scale motion, potentially augment motion, extend the capability of the surgeon, help them navigate, help them anticipate, well, warn them, guide them, and in the future potentially automate. So you can see how the power of this concept could be taken forward, and that's essentially what we do. So come by the booth 219, and we'll tell you some more.